Today we are going to see Introduction to Computer Controller Processes, Part 13, 18th webinar. Uh, in this session, we are going to see how to design a deadbeat and Darlin's controller, and we are going to see how we can simulate this on Simulink platform. Day before yesterday, we have seen that how to simulate deadbeat controller. Today, we are going to design a Darlin's controller and how it can be simulated using Simulink platform. First of all, let us once again see first of all, let us once again see how to design a deadbeat controller, and then let us see how to design a Darlin's controller, then how to simulate them in the MATLAB Simulink platform. First thing is what we have to do is here we want to simulate a higher order system, fourth order system, that is 1 by s plus 1 to the power 4. This is very important because no system in the world is first thing. Even though if it is higher order, its order will be increased because of other components in the loop. All components in the loop will be included so that the order of the system will be not less than 5. But it's not possible to find the exact mathematical model of the process. It's not possible to find the exact mathematical model of the process. That's why we are going to get the approximate mathematical model from the experimental data to design the controller. This is the usual practice. For that, we have to get the open loop step response, say reaction curve as shown in figure. Notice that this is the reaction curve for the given 1 by s plus 1 to the power 4. We got the reaction curve. From this, we got the dead time as 0.7, and the time constant including dead time is 3.259. Time constant plus dead time equal to 3.259. That is time taken to reach 63.2% of final value. Minus dead time gives the time constant, that is 2.6. And the gain, here we gave unit step change, it is settled at unity, therefore gain Kp equal to 1. Now we can model this as first order plus dead time as Kp e power minus TdS upon TPS plus 1. That is, dead time is 0.7, gain is unity, time constant is 2.6 s plus 1. Now this is called GP of S. GPM of S, not GP. This is model. This is not the exact process, the mathematical model of exact process. Equivalent first order plus dead time model. That is e power minus 0.7 s upon 2.6 s plus 1. This can be called as GM of S. This is required to design controller. Always model of the process is required to design controller. But this is a continuous process. That's why it should be preceded by a first order hold. Therefore, HGM of S. Instead of P, I am selling M because we are taking model 1 minus e power Ts upon S, e power minus 0.7 S upon 2.6 S plus 1. If you obtain the HGP of Z, it looks like this: 1 minus Z power minus 1 for this part, and for this part, it can be taken as one sampling period because we are assuming that sampling period equal to 1 second. This is less than 1 second. Let us approximate this to 1 second. Therefore, for this, this can be replaced by Z power minus 1. This can be replaced by 1 minus z power minus 1. The remaining term 1 by s multiplied by 2.6 s plus 1 can be written as this. The remaining part can be written as like this. Therefore, from the table we can get the z transform for 1 by s multiplied s plus a. By using that expression, we can find 1 minus e power minus 1 by 1 by 1 upon 2.6 z power minus 1, 1 minus z power minus 1 multiplied by 1 minus e power minus 1, 1 by 1.2.6, because a equal to 1 by 2.6 z power minus 1. If you simplify this, you got HGP of z as 0.32 z power minus 2 upon 1 minus 0.68 z power minus 1. Now we got HGP of z. Now we can design uh, the deadbeat controller. What is deadbeat controller? D of z equal to 1 by HGP of z. Just now we got HGP of z, inverse of that 1 by HGP of z. Then y of z by y set point of z. Here, dead time is 0.7, approximated to one sampling period 1, plus as per design criteria we have to add plus 1. Therefore, z power minus 2, y of z by y set point of z power minus 2, 1 minus y of z by y set point, another z power minus 2. If we simplify this, we got like this. Now we have to check whether it is physically realizable or not. For that, we have to convert this function such a way that the denominator has one constant term. Then the numerator should not contain any positive powers of z. Yes, it does not contain any positive powers of z. Therefore, it does not contain any positive powers of z when denominator has constant term. Therefore, this is physically realizable. Then d of z can be written in positive powers, because in Simulink we have to enter positive powers. That's why multiply the numerator and denominator by positive powers of this lowest, that is z power 2. So if you multiply the numerator and denominator by z power 2, you will get z square minus 0.68 z upon 0.32 z square minus 0.32. We got this is d of z. The poles are 1 and minus 1, which is on the unit circle, that is equivalent to 1 by s term. This is in open loop 1 by s. But if find the closed loop, it becomes first order system. That's why this will be a stable controller. Now we have to design a Simulink block like this. This is a step block, summing block, the digital controller, zero order hold, fourth order system, scope. All you have to get and connect like this. The fourth order system can be written like this by using this triangle s power 4 plus 4s cubed plus 6s square plus 4s plus 1. This has to be entered. Then we can simulate. Now let us simulate this first. This is the step function, the summing block, and discrete transfer function, zero order hold. Then transfer function is continuous transfer function, and scope. These are all taken to simulate this. First, the discrete transfer function, we have to enter the transfer function of z transfer function of that digital controller, that is 1 minus 0.68 coefficient of z, then no constant term, that's why 0. Then if you consider the denominator 0.32 z square, 0 z minus 0.032, constant term is 0.032. The sampling time is 1 second, that's all. Now we have to enter 0 order fold. In that we have to enter only sampling period, that is 1 second. Then transfer function we have to enter fourth order 1, 4, 6, 4, 1 are the denominator coefficients are entered. That's all. Now we have to simulate. To simulate, we got the response. Yes, we got the response. It has large overshoot and oscillations, but we have large overshoot and oscillations. Even at this is simulated for 100 seconds. In that, if you notice that if you see amplified version, even at 90 seconds, you can notice that the oscillation. The amplitude may be very small, but always it has the oscillations that we have to notice. Even here, oscillations are there. This is the drawback with the deadbeat controller, but there is no steady state error. Oscillations are there. It is subjected to oscillation. That is drawback, but no steady state error, but large overshoot. Now let us simulate the Dolin's controller. The Dolin's controller, the assumption we made in the Dolin's controller is the response is a first order response with the dead time. This is the response we are assuming in Dolin's. So this dead time is assumed as theta. The time constant is assumed as mu. These are the two assumptions we made. But actually, mu is the design parameter. Theta should be greater than the dead time, actual dead time of the process, k times sampling period plus 1. Always this theta must be greater than or equal to kt plus 1, where k is the integral multiple of sampling period equal to dead time plus 1. And the gain kp, of course, is required. Kp is always 1 because we are giving a unit step change and we are assuming that it is settled at unity. Therefore, kp is 1. Now, to design the digital controller, this model can be used for our design. What is that model? We are assuming that the response is y of s. The response equal to the assumption we made is 1 upon mu s plus 1. Mu s plus 1. That is the assumed time constant, design parameter, mu s plus 1. Gain is unity, e power minus theta s, that is dead time, multiplied by 1 by s, because we are seeing for step response 1 by s. So this is the response of the system in time domain, Laplace domain. This is the response of the system. From this, we are taking this way. From this, we got this. So now we have to find y of z. For this, we have to find y of z. Y of z for this, if you obtain, this is what e power minus k s. So it can be minus k s. So it can be written as kts. So it can be written as e power it can be written as z power minus k. This theta can be written as kt. Therefore, if you take z transform, you will get z power minus k. And this, if you obtain z transform for this and divide by y set point of z. What is y set point of z? Y set point of z is 1 by 1 minus z power minus 1. Here you will get one term 1 minus z power minus 1, and for y set point of z you will get 1 minus, because it is in denominator comes to numerator, z power minus 1. These two getting cancelled. Therefore, y of z by y set point of z, you got this. Here k unspecified, mu unspecified, sampling period unspecified. If you substitute this in a digital controller, what is a digital controller? D of z equal to 1 by HGP of z. HGP of z. HGP of z multiplied by y of z by y set point of z. Y set point of z whole divided by 1 minus y of z by y set point of z. Y set point of z. So if you write like this, this you can substitute here and here. If you substitute this and HGP of z also you substitute, you will get d of z. So the final expression for d of z is, for Dahlin's controller, this 1 by HGP of z, numerator 1 minus e power t by mu. Mu and t are design parameters, z power minus k minus 1, and 1 minus e power 1 by mu z power minus 1 minus 1 minus e power minus t by mu z power minus k minus 1. So here, if you substitute the value of t and mu k, you will get to the digital controller if you know HGP of z. So once you know t, mu, k, and HGP of z and HGP of z, all these four if you know, then we can design the digital controller. We can design the digital controller. Now let us design the digital controller for the given process 1 by s plus 1 to the power 4. We assume that sampling period is 1 second. Mu equal to 3 we are assuming. Mu equal to 3 we are assuming. And the mathematical model of given fourth order process. What is fourth order given process? 1 by s plus 1 to the power 4 has to be controlled. But what is the mathematical model of that process from the experimental data? E power minus 0.7s upon 2.6s plus 1. So theta equal to 0.7 plus 1, that is equal to 0.7 plus 1 equal to 1.7. If you can approximate this to 2. So k equal to 2. So we got k equal to 2, t equal to 1, and mu equal to 3. For that, we have to design the controller. So we are assuming that t equal to 1, mu equal to 3, and the process is 1 by s plus 1 to the power 4, and the model of the process is e power minus 0.7s upon 2.6s plus 1, and theta equal to 0.7 plus 1 we have to take. Therefore 0.1 plus 1.7, k must be integral multiple of sampling period, therefore 2, k equal to 2. For that we have to design the controller. Then d of z equal to 1 by HGP of z, 1 minus e power t by mu, and these values we have to substitute here. So we substituted all these values. Already we got HGP of z for deadbeat controller. This is HGP of z for deadbeat controller. This value can be used to design Dahlin's controller. 0.32 z power minus 2 upon 1 minus 0.68 z power minus 1, that is substituted here. The same value substituted here for 1 by HGP of z, and substitute t equal to 1 and mu equal to 3, k equal to 2. If we substitute, we got this. Here e power minus 1 by 3 equal to 0.717, and 1 minus e power minus 1 by 3 equal to 0.28. Substitute all these values, you got d of z. You got d of z. So that is d of z equal to d of z, that is digital controller, equal to 0.28 z power minus 1 minus 0.19 z power minus 2 upon 0.32 minus 0.23 z power minus 1 minus 0.089 z power minus 3. Here we have to check whether it is physically realizable or not. For that, the denominator must contain a constant term. Like that, you have to adjust. Here, what is the highest degree? Here you got z power minus 3. Here you got z power minus 2. So multiply the numerator denominator by z power plus 2. Here the first term is z power minus 2. Here next term is z power minus 3. Z power minus 5 you got. So multiply to get a constant term, multiply the numerator denominator by z power 2. So you will get this type of expression. Now this can be checked for physically realizable. What is the meaning of physically realizable? If this is the controller, means if you cross multiply this, what you will get, here d of z equal to what? M of z by M of z, controller output by E of z, error of z, error. So if you cross multiply this, what you will get is 0.32 M of z, 0.32 M of z. This is M of z minus 0.23 z power minus 1 z power minus 1 M of z, M of z minus 0.89089 z power minus 2 M of z, M of z, like that we have to write, equal to, you have to bring E of z here to the right hand side. So what you will get, 0.28 z power minus 1 E of z, E of z minus 0.19 z power minus 2 E of z. So now what is the meaning of z power minus 1 M of z? Previous controller out. What is the meaning of z power minus 2 M of z? The same old controller output delayed by 2 sampling period. What is the meaning of z power minus 1 E of z? Old error, previous error. What is the meaning of z power minus 2 E of z? Error delayed by 2 sampling period. So from this, all are available data. Old controller output available, old controller output available, old error available, old error available. That's why M of z can be calculated. Divide on both sides the 0.32, you can calculate M of z. Therefore, it is physically realizable. How we can say directly, the denominator must contain a constant term. That time, all must be in negative powers. The numerator should not contain any positive powers. That's all. It should not contain any positive powers. Yes, it has some constant term, does not contain any positive powers. Therefore, it is physically realizable. Then we have to enter this controller in Simulink block. For that, it should be in positive powers. Therefore, here the lowest degree is z power minus 3. Therefore, multiply the numerator denominator by z power 3. If you multiply this, you will get, if you multiply this z power 3, you will get z square, z cube square, and the constant term you will get. The denominator polynomial is the here. If you see the roots of this polynomial, we got all terms are in the unit circle. All poles of the controller are within that unit circle. Therefore, it is a stable controller. It is a stable controller. In the z plane, real and imaginary axes are taken, um, it is a stable controller because all poles and zeros are within that unit circle. Now let us simulate this controller. To simulate this, uh, we have to take this is the Simulink block to simulate Darlin's controller. In that, we have to enter step input because we are going to check the servo response for that. This is the discrete transfer function block, zero order hold block, transfer function block, scope, summing block. That's all. Now we have to enter the controller. What is the controller? For mu equal to 3, the controller is 0.28. The controller is 0.28 minus 0.190 because no constant term, that's why 0 we entered. Denominator 0.32 minus 0.23 minus 0 because no z term, and therefore constant term is minus 0.089. This is the controller we entered. We entered the process also, fourth order 14641 coefficients of denominator polynomial we entered. And the zero order hold, the sampling period is 1 we entered. Here also we have to check the sampling period, that is also equal to 1. That's all. So we entered everything. Now let us simulate the servo response and check that step input. The step time is 0, the final value must be 1. Okay, now let us simulate. This is the response of for servo response for Darlin's controller. Note that there is no large overshoot, no that much oscillation, as we have seen in Deadbeat Controller. If you compare both responses, this is the Deadbeat Controller. If you can see here both, yes. This blue one is the response due to Darlin's controller. The yellow one is response due to Deadbeat Controller. You can notice that Deadbeat Controller gives large overshoot and the oscillations. The blue one gives no, not that much oscillations, but you can notice that we gave a deliberate delay in the response that is there because we assume that the response is first order plus dead time. We deliberately gave theta dead time here. That's why it starts here. That you can notice. No large overshoot here. It quickly settles than Deadbeat Controller. But one thing you can notice here that you notice that even though the Deadbeat Controller has oscillations to steady state, there is no steady state error. The small oscillation, this can be ignored. Small, the amplitude of oscillation is very, very small. This line is 1.02. This line is 2%. This oscillation can be ignored, but anyhow, oscillation is there. But notice that the Dahlin's controller has Dahlin's controller has steady state error. Notice that Dahlin's controller has a steady state error. But the deadbeat controller doesn't have any steady state error. That is one important thing that we have to notice. Otherwise, this is better. Now let us check the regulatory response for this process. For checking that regulatory response, we have to give disturbance. Anywhere you can give, but let us give disturbance here. Okay. Step disturbance is given here. Step disturbance is given here. Let us give positive disturbance. Positive disturbance. And the same can be copied here and now we have to give disturbance. Copy this and just here. Give to both. We are going to give disturbance here. Yes, disturbance is given. Now we gave final value is 1, step time is 0. No servo response, that's why we'll make the final value here 0. And here also we'll make final value equal to 0. So if you simulate, what you are getting is, this is the regulatory response, load response for using deadbeat controller. This is the load response, regulatory response using Dahlin's. No, that much oscillation. That is also you can notice. Let us compare both in this. You compare these two. The blue one is for Dahlin's and the yellow one is for deadbeat. You notice that Dahlin's controller has large overshoot as far as load response is concerned. It has large overshoot. Notice that we designed the controller for servo problem. What we designed, we are assuming that y of z by y set point of z is a first order plus dead time response. We didn't do any assumption for load changes. That's why it is not designed for load changes. Obviously, it has poor performance for load changes. But for servo response, it gives better response than deadbeat controller. But anyhow, it doesn't have any oscillations like deadbeat controller. It doesn't have any oscillations like deadbeat controller. Doesn't have any oscillations like deadbeat controller. You see here, one more thing we have to see here. It also has steady state error. It also has steady state error. And the Dahlin's controller has steady state error. Notice that deadbeat doesn't have that much oscillation here for load changes, as we have seen in servo response. So these are the points we have to note during simulation of Dahlin's controller. So in a nutshell, what and all we have noticed, if you see the servo response, if you compare both, the deadbeat controller has large overshoot and oscillations, but Darlin's controller does not have that much oscillation, but it has steady state error. Another thing is the response, there will be a delay in the response for that Darlin's controller. That is, we made deliberately in the assumption while designing the controller. The assumption for designing the controller, we made a deliberate delay. That's why we notice some delay in the response. On the other hand, if you see the regulatory response, um, the Darlin's controller has large overshoot because it is not designed for regulatory response, but deadbeat controller gives better response, even though it doesn't have that much oscillation as we have seen in servo response. Now let us design Darlin's controller for other new values. Now we designed the Darlin's controller for mu equal to 3. Now let us design Darlin's controller for mu equal to 10. Say the sampling period is no change. All others no change. Model same. Only thing is we have to change the mu value in that part. That's all. If we change these mu values, we will get the controller like this, T of Z. Here also we have to check that physically realizable. That's why denominator must contain, all must be negative powers. That time the denominator must contain a constant term. When it has a constant term, the numerator doesn't have any positive powers. Therefore, it is physically realizable. The lowest power is z power minus 3. Therefore, multiply the numerator denominator by z power plus 3 so that it will be in positive powers of z. It is convenient to enter in Simulink module, Simulink controller, Simulink block. We can easily enter this in Simulink block. That's why we made this into positive powers. Now we have to check the roots of this denominator polynomial. If you check the roots, 0.7245, 0.45 and minus 0.28, all are within that unit circle. Therefore, it is physically, stable controller. So we can simulate this. We can use this controller for simulation. Next, now we will design a controller for mu equal to 1. All values are same except this mu value. If you change, you got a controller like this, d of z equal to this. Keep one constant term in the denominator while writing numerator denominator negative powers of z. So no positive powers in the numerator. Therefore, it is physically realizable. Denominator, if you see that physically realizable, that lowest degree is z power minus 3. Multiply the numerator denominator by z power 3. You will get in positive powers of z in the controller. This can be convenient to enter in the Simulink block. Now, if you check the roots of this denominator polynomial, are within that unit circle. Therefore, it is a stable controller. Now, let us simulate for all the three deadbeat controller. One for mu equal to 1, another one for mu equal to 3, another one for mu equal to 10, and a deadbeat controller. Let us compare all the four. All the four. Here, the controller we have to enter is mu equal to 10. That is 0.095 z square minus 0.065 z, and the constant term is 0. That is numerator. Denominator 0.32 z cube minus 0.289 z square, and the z term is 0, and the constant term is minus 0.03, and the sampling time is 1. So this is ready for simulation. This digital transfer function acts as a digital controller. Its sampling time is 1, and now we have to check zero order hold. It is also having sampling time of 1. transfer function, it is fourth order system 14641. Now we have to include step input for servo. So let us connect here why we have to have separate step function. Here also it can be removed and it can be connected here, so that for all controllers this one block will give set point. And one more controller we have, one more simulation is here. Here also this also can be given from here, and we have to check whether it has that controller for mu equal to 1.32 z square minus 0.429 z, and the constant term is 0. Denominator 0.32 z cube minus 0.117 z square, and constant term z term is 0, that's why 0, and the constant term is 0.202, and the sampling period is 1. Yes, so we got all controllers ready. Zero order hold, sampling period is 1, and fourth order is entered here. Now we can simulate all these controllers. So already we simulated for mu equal to 3. Now let us simulate for mu equal to 10. This is the response for mu equal to 10, very sluggish. If you see the response for mu equal to 1 smart. Now we'll see all together in one window, one scope. Let us see all together. So you have to connect this, and you have to connect this also. Yes. Now we can see all in one scope. Yes. This yellow one is deadbeat controller, and this blue one is mu equal to 3. This green one is mu equal to 1. That red is mu equal to 10. If we increase the time constant, design time constant, it becomes sluggish. Mu equal to 10, very sluggish. Mu equal to 1, very smart. If you go on increase mu, it moves towards the deadbeat controller, but without that much oscillation. Without that much oscillation, we can make this. Now it's better than, it settles quicker than deadbeat controller. It has less oscillation when mu equal to 1. If you see the mu equal to 3, it doesn't have any overshoot, as well as it also settles better than mu equal to 1. Therefore, mu equal to 3 gives better response. But the raise time is less. That is the only difference. Raise time is less when compared with the green. If you see, all Dahlin's controller starts after one sampling period, because we two sampling period, because here you can check that. You can check that here. You can check that here. All starts here after two sampling period. So this quickly raises. All others are starting after 2 sampling period, because in the design we assumed that it has dead time. And the response has dead time. That is the assumption we made while designing the controller. And notice also that all has steady state error. That deadbeat controller doesn't have any steady state error, but oscillations. Mu equal to 1, it also has steady state error, but very small. Mu equal to 3, further steady state error. Mu equal to 10, large steady state error. If you compare, less than 5%. So this is 5% line. This is 5% line. Within that 5%, maybe 3%. This is 1%. This is 0.5% like that. So anyhow, steady state error is there. Steady state error is there. For accurate control, it won't give that zero steady state error. That is the drawback with the deadbeat control, the Dolin's controller. Dolin's controller gives steady state error, but it doesn't give any oscillation. It doesn't give any oscillations. Now let us do regulatory response. For regulatory response, we have to give load changes to this and this. Load changes given. Now let us make servo equal to 0 and 0, and let us give load change. Load change. Final value 1. We are giving a positive load change. So see the response. Deadbeat is better than all other knowledge controller. As far as load change is concerned, deadbeat is better than all other controllers. Even there is no that much oscillation even at the steady state. You see here, amplify. The yellow doesn't have any oscillations here, as we have seen in servo response. And there is no steady state error. That is also very important. But the green is mu equal to 1, it has steady state error, small steady state error. Blue, mu equal to 3, it is also having a steady state error of 1%, 0.5%. It has almost about 3.5% steady state error. So the Dolin's controller has steady state error. Dolin's controller has steady state error, but the deadbeat controller doesn't have any steady state error. And the deadbeat controller works very fine for load changes. It does not have that much overshoot also. No oscillation, no overshoot. So as far as load change is concerned, deadbeat is better. As far as servo response is concerned, Dolin's is better. That is the conclusion we can make from this. In the same way, we can do negative load changes also. If you do negative load changes, we have to enter -1 instead of +1, -1, and see the response. The response is like this. So here also the deadbeat controller gives better response. We'll compare with all other controllers. But the Dolin's has steady state error. Deadbeat doesn't have any steady state error. That's all. So what is the final conclusion? As mu increases, the response becomes sluggish. Here, mu equal to 10, the response becomes sluggish. Mu equal to 3, little bit smarter. Mu equal to 1, smarter. And this will approach the response of even load response also better if you select small mu value. That's why so by selecting small mu values, we can design load response similar to deadbeat. That we can conclude.